regarding the postfix, how do we use the postfix? And what the postfix means is these two backslashes. Well, let's say we define an array or a vector, just like that. And now I would like to display it as matrix, right? We can just use matrix form, put that postfix, and it will give us the matrix form. And postfix is practically identical to this form of notation. And if we just wrapped the whole thing in matrix form, we'd practically get the same thing. It's akin to working with pipelines in Linux. It just pipes it into the function, right? Well, another thing about Mathematica is that anything can be used as a symbol. That is, let's graph it using 3D. Let's create a red sphere, right? And let's give it an image size of 30. We get this beautiful small light sphere, and we can just use it as a symbol. For instance, expand 1 plus b cubed. We get this. Wait, so let's make it a little harder. We get this. But we can practically also say 1 plus this small sphere. I just selected it and copied it. Cubed. And we get this beautiful answer. Now let's move towards replacements. And what are replacements and how does it work? For instance, you have an expression of ax plus b plus bx. And let's just clear the definitions of a and b and x. And this is just ax plus bx, right? This is just ax plus bx. And for instance, you'd like to substitute some numbers into it. That is, you place a slash, then dot afterwards, and you say, I'd like the a to be 3, and I'd like the b to be 5. And as a result, it substitutes these variables into that expression. Expression itself does not change, but you could have also changed the way you defined the expression. And let's say 10 and b 20, in which case the expression would take this value permanently. And this is practically the essence of the replacements. Just take some expression and we'll substitute some values into it. It's very simple. Now, let's go over a simpler example. Let's clear the variables again. I mean, more comprehensive example. And let's say we have ax plus bx. Then we substitute a for b. And then we substitute again b for c. B for c, by, right? And so the reason we get cx plus cy is that first, b is c, right? This evaluates first. Then this b becomes c, and a then becomes b, and as a result a and b are c. For instance, well, we can go over the quadratic equation and verifying its solution. For instance, let's clear the variables again, a, b, and c. And x squared, and this equals to 0, and we solve it in terms of x. We get the solution. We get two solutions for the quadratic equations. And afterwards, if we want to verify the solution is right, we just say x squared plus bx plus c equals to 0. No, not equals to 0, but yeah, equals to 0. Then we'll substitute the solution into it. The solution got substituted into the whole thing, and at the moment it's not apparent. Does the inequality hold? And in order to determine if it does hold, we just need to simplify the whole thing. And this is the function that does it. That does the simplification. And just like before, to get this entire previous input, we can just enter a percent sign. As you can see, the first inequality evaluated to 0, and the second one evaluated to 0 as well, which means the equations hold and they are right. Now we need to talk about the functions, and the way we define functions is that first we write the name of the function, for instance function name a, and then you write an argument. The function name can be anything. Let's just say it's just f. Then we write an argument which needs to have this underscore afterwards. That's only during definition. Then we have this semicolon, equal sign, and 0.2, let's say, cosine 0.3 multiplied by x squared. This is our function, right? We have the expression on the right with a variable. We have the function itself, where we defined what the function takes in as an argument. In our case, this is x. And then we have this colon, equal sign. And now we can use it if we want to. F3. As you can see, we just say f, then we add or input whatever number we want, and we get the result. If we wanted to plot the derivative of the function, it's very simple. Just add this apostrophe, and you just add the tick, and you plot it from 0 to 10. And that's the plot of the derivative of the previous equation we have defined. And the definition is not limited to a single number of arguments. That is, you can have two arguments if you want. Then we can reuse the function we just used. And as you can see, as soon as we define the argument we take in, we don't really need to add that underscore afterwards in the expression itself. So negative 0.3 y squared. This is our equation. Now let's just try to plot it. That's a 3D equation, so plot 3D. G, x and y, and x can be from -2 pi and 2 pi. Y will be from -2 pi and 2 pi as well. Wait, pi, yeah, here it is. Now we plot it and we get this. So we can change it to 2 pi and y. This practically 3D, yeah. And range, let's just fix the range. Plot range O, and we get our 3D graph. And this is it. Wait, there's also the lists, right? So let's just go over the lists in a little more detail. And let's say we have a list, and the way we define them just like we did before, but you can use a sign in and cosine in. That's the pair we're going to be generating, and we're going to be iterating from 1 to 20. This is practically what this part means. This is the sequence we are iterating over, and then we use this AND, which goes from 1 to 20 for this sequence. And as a result, we get this. We can plot it if we want. So we can use list plot, list 1, and we get novel. Now, another thing, yeah, I did show the matrix form, and this is it, yes.